Hi everyone, let's start. Welcome back to the tinyML talk of today. We have the great pleasure to host Brenda and Greg from MathWorks, and they are going to talk about the tinyML approach to deploy reduced order model of complex system on microprocessors. But before to leave the floor to Brenda and Greg, let's remind that all these talks and many other events in tinyML are possible thanks to the great support of our strategic partners, which are committed to make happen these and other events, which are very important for the tinyML community. They are AI-Zip, Analog Device, Arduino, ARM, BrainChip, Impulse, GreenWaves Technology, Grover-T, IBM, ImageBob, Infineon, Innatera, Microsoft, Note AI, NXP, Polytechnology, Quixo, Qualcomm, Renesas, Schneider Electric, Sensimil, Sony, Silicon Labs, ST Microelectronics, Synaptics, Symbian, and TDK. There are a couple of things we need to remind all together. First of all, Meetup. Meetup are a great assets in order to let the community to meet at local level and at the global level and share the latest advancement on the tinyML subject. That's a vibrant community, rich of members, close to 16K, and well spread across the planet. The other great assets is the LinkedIn page where you can interact and get updates from over 4K members, which are followed by a lot of people, and you can learn a lot from following this page. So if you are interested, please make sure that you stay up to date. And then, since 2018, the community created, the foundation created a great YouTube channel where a lot of resources, including this video, will be stored and are stored, so that you have always the chance to go back to what you missed and learn from the great content we are sharing. And this is a great content because there are more than 600 videos. With a lot of topics around the tinyML subject that you cannot miss. And then quick reminders, slides and the video will be available soon through the tinyML forum and the YouTube. If you have questions, and please, I encourage you to pose many questions to Greg and Brenda. There is the Q&A box window below, and so please type in your questions, and we do expect a lot of interactions with you. Before to leave the floor to Brenda, let me introduce Brenda Zhuang. Dr. Brenda Zhuang is a consulting engineering manager at MathWorks, where she leads a team responsible for software tools for automatic deployment of embedded applications such as motor control and deep learning to microprocessor and FPGAs. Brenda joined MathWorks in 2007. She received her PhD from Boston University in system engineering. She served on the technical program committee in control theory, modeling, and simulation. With Brenda, there is Greg Coppenrath. Greg is the product marketing manager for Fixed Point Designer and Deep Learning Toolbox Model Quantization Library. He has experience in the development of embedded system product development in the semiconductor industry. He received an MBA from Worcester Polytechnic Institute, the Master in Electrical Engineering from University of Massachusetts Lowell, and received the Bachelor in Electrical Engineering from WPI. So I leave the floor to Brenda and Greg, and let's hear from them in this great talk.
Thank you very much, Danilo. Thank you for your well introduction and warm welcome as well. As many of us who work in the engineering discipline, the first principle modeling has always been the tools we use to understand the systems that we work with and explain their behaviors. It works great because it can help you bring in the insights, as well as we can tweak different type of parameters for us to understand all the simulation output. But at the same time, we all recognize this is a very time-consuming process. We need domain expert in order to perform those first principle modeling correctly. Now, today, we wanted to show some of the approaches you can really use the artificial intelligence, or more specifically, the data-driven approach to solve similar problems that you've seen in the complicated systems you do. And also, we would like to introduce you on some of the tinyML approaches that now we have available in our toolsets, being able to facilitate the deployment process. Thank you so much for joining us. So today, Greg and I will walk you through some of the interesting steps. Both of us are coming from MathWorks, and we're happy to really introduce ourselves to the tinyML community and walk you through the topics today. So who is MathWorks? Many of you probably fondly remember us being the creator of MATLAB and Simulink. MATLAB is a programming environment that has facilitated data analysis and visualization. Simulink is a block diagram environment that can use for designing, simulating, testing, and deploy your systems into real-time platforms. And as many of you probably know, we have many collection of toolboxes that handle specific tasks. We also have a very vibrant community that has community contributed toolboxes that deal with even more specific data handling, including geoinformatics or different kind of data analytics in scientific field. That's because all of our users and customers are engineers and scientists just like you. And for many of the embedded systems that are sitting next to you, like your smartphone or like the automotive, your vehicles you're driving in today, or maybe the airplanes you're taking, a lot of those design tasks are driven and done in the tools of MathWorks. So we're a global company, and we have offices almost across the world, and probably you can find one that's pretty near to you. And Greg and I are both actually now, sits, as you can see from outside my window, in Natick, Massachusetts, United States. So it's about 11 o'clock here in the East Coast. In overall of this company that we are still private, that leaves us a lot of room to really invest in what we see are the mega trend of technology field. So for example, specifically today, we'll touch upon how artificial intelligence as a data-driven design approach can use to solve real-world problems. So with that, we're going to break today's conversation into kind of three major parts. I will cover the first two, talk a little bit about how to apply reduced order modeling methodologies to a complicated design problems, and then show how you can take this design data-driven model with the AI methodology behind it into a target deployment. Greg will specifically handle the challenges of now you want to take this design to a much more energy and cost-constrained target, such as a microprocessor. What are the additional design steps you can take in our shipping tools? We'll be walking through some of these steps with an example. This example is, if by looking at it, it's a driving scenario where you can have a driver, have the controllers for the vehicle, and also the full model of a passenger car. The ideas we're trying to is replacing some parts of this particular design questions using the AI-driven design approaches, and being able to really show how the full systems are being able to carry through in the design exploration stage. Before I jump into the actual details of how to perform this particular workflow steps, I want to be able to first handle three major concepts. At least clarify what do we mean by this context. The first one is model-based design. The second one is what do I mean by AI-driven design, system designs in this context, and also what kind of reduced order models that we're going to be looking at today. So model-based design is really a systematic way of applying models across the different stages of a large system design tasks, like what we see here. This is probably very familiar with to many of you because you must have played tons of it, or you're the system architect for a lot of this. The architecture aspect is mostly being able to capture the behavior models and the functional specification. In the design phase, the systems and subsystems, or sometimes called components, can be described either with a physics-based formulas, methodology, or approaches. In this case, we can call it first principle modeling elements, or they can be approached with the AI or the data-driven approach. The algorithms that in many times is going to be going onto the edge device or the target needs to run efficiently on any one of those implementations, spanning from CPU or microprocessors all the way to FPGAs or even PLC. And then this iteration can then continue to improve on the integration and testing part. And this is iterative process, and the closed loop design environment is what we consider as the workflow for model-based design. So what does AI elements factor into this one? So I have a little box over here. Let me just resolve it so that I don't block my view. That is by taking the design-specific tasks and then use AI approach to take a look at it. So what is the typical data-driven design stage that translated in our work in this case? You probably have seen this kind of 4 major steps in many other platforms where you work on a data-driven design approach. You start with data, and then selecting of the model, being able to simulation and test with your validation data set or actual real world data set, and then being able to see how suitable it is and what is the necessary crucial steps taken to deploy it. It's important to note that this process is not linear. Usually it's iterative. Sometimes, many times it's because at a later stage, you find out there are additional requirements or tweaks or changes, or even sometimes optimizations that you have to take ahead of time. So this really emphasizes how important to have a tooling and tool sets in order to be able to perform these tasks in a fluid way. The last concept, as I promised, that we need to think about is how do we introduce the model and the dimension of the model into this design? So in the first 2 parts that I will cover, I'm going to more focus on using the AI approaches for component modeling. So the end point for me is being able to speed up the desktop simulation and being able to run it on the real-time hardware. The second part that Greg will cover will focus on using the AI models that produce to represent algorithms and really talking about how at the deployment level, what do we need to do in order to replace a physical system, for example, with a virtual design element. So now if we stay focused on the first part, we're doing the component modeling, we can introduce the third concept, as I mentioned. What do we mean by reduced order modeling? It's really a set of techniques that we can use in order to reduce the computational complexity or the storage requirement for a compute model. And in this case, the reduced order models will be able to preserve or being able to as close as possible to the expected fidelity of the original model, in this case with a controlled error. The benefits is quite clear, right? Because you do want to solve a simpler problem if the new problem is being able to represent what was the original design elements. Also, this also make it feasible to take this simulation model, in this case, reduced order model, into real-time hardware, so you can really run it faster, and sometimes it's feasible to run. And as I mentioned, if you're really taking the similar approach and put this lens against the algorithms, then we're looking into even more efficient implementation of edge elements that we can use to work as the digital twins or the virtual sensors. And that's why a lot of this design element can be put into this framework. So let's translate a little bit more how this is done. Again, this is not a new concept. This has actually always been ingrained in our engineering design elements. Many of the parts that you're already very familiar with, including using physics-based models or using mesh in order to approach an underlying physical model with a model. And that's already a reduced order. In this case, for example, the pictures I show over here is coming out of our Simscape electronics in order to represent the information. And then with a nonlinear model, especially complicated nonlinear model, you can always linearize it with one or multiple operating points. Now, as I previewed, in today's approach, we're more interested in looking how we can approach this problem using the data-driven approach. Even for that, again, we have traditional methods, very much like a static method, what we would call, to replace that, to represent the original complicated system or higher order systems with, say, for example, lookup table or surface or curve fitting. Today, we're going to be focused more on the dynamic ways, but really looking into how to take the input and output of the original systems and use it to build up a deep learning and machine learning models in order to represent the same dynamics. There's many more tools. As I mentioned, MathWorks has many tools, and we've been building in this area. So you can find the toolboxes and the relevant methodologies in our documentation as well as technical articles. Now we establish what are the focus of this, and then how we wanted to draw this contrast between the original, more high fidelity, large scale models that we used by capturing the first principle versus the data-driven models. This part probably is quite obvious to you now, because the white box approach means if we have the right domain expert, we'll be able to describe it at the level where it's really tied to what my simulation output or your design goal is. When we're taking the data-driven approach, we're going to use statistical method, optimization method, and also some of the artificial intelligence method in this case. That means we're really looking at the data as a black box, and your output or your constructed model will only be as good as what your data was telling you. So that's probably why you want to require a lot of data to do it. And the outcome of that model sometimes does pose challenges in it's harder to interpret and it's very difficult to explain. So these two types of modeling strategy or approaches are not contradicting each other. Actually, they coexist. So this is how we can show in the model systems that looks like this. In this case, we have multiple elements. In this particular example, we're going to want it, the goal is to be able to capture the output of the vehicle velocity from the driver's action. So that's why we'll be able to simulate the driver without actually simulating details pressing down the gas pedal, but we'll bring in different kind of elements for that. The car, in this case, the vehicle dynamics at this point are almost fully described and modeled using the first principle. So in the coming few steps, what we'll take is to break down the car model. Instead of taking the engine model in this case, which can be described again as first principle, we're going to replace this with this high fidelity complex model with deep learning model or AI model is how I have been calling it. So that means I'm going to bring over this white box simulation into a black box version. And for the purpose of illustrating the steps, I'm going to set it up so that the input will be capturing 4 different parameters in this case, and I'll use this to predict the output of the engine torque. So taking this high-level algorithms, we're going to go through with the first step, right? This is the bottom part. You see the breadcrumb of the 4 steps I showed as an AI-driven or data-driven approach to model our elements in this case. So let's start with data preparation. As you may know, there are many different ways to do it, including using the real-life data. But specifically in this case, we're going to use the simulation, as we see here, with a bunch of parameters that we can sweep through in order to gather the synthesized data. It's pretty easy to do that when you're finding yourself in a modeling element like Simulink. In this case, we can start out by running the simulation with an extra first principle model, engine model. And then by sweeping through different kinds of parameters, we can lock down the data. And most importantly is we already pre-selected type of features we're interested in, and we can collect the quote, synthesize the ground truth of response. So this is a quick screen recording of how we're going to do that. I'm just going to let it play and I'll walk you through the key steps in this case. We set it up so that we can have the synthesized data, in this case, using a parameter sweep. You see that little table popped up there. We set up this, what we call the design of experiments. And ultimately, the key elements is being able to run many simulations, given the data set parallelly. And we wanted the answers to come out on the other end, where we could organize this data for our training and testing purpose. So this is the whole loop of the synthesized data elements. So specifically, we're going to bring up a model. This Simulink model will have the ability to capture those parameter sweeps, as well as being able to bring them up into what we call the simulation manager. The simulation manager tracks how many different kind of simulations are happening at the same time. It starts out all gray when we're setting up the parallel computing environment. The blue means this is now actively worked on in a worker, and green indicates the simulation is completed. Of course, you probably noticed that we're using this animation in a speed up fashion. So at the end, we'll get all the simulation run completion. And then now remember that those are the logged data that I'm mostly interested in. So I will be able to store this information in a data format. It's called mat file in MATLAB. Now we have the data. We wanted to go ahead and select a model, as we shown in the step 2. In this case, we talk a little bit about the static approaches versus the dynamic approach. So if we zoom into the dynamic approach for today, I want to be able to cover the approaches of either using an LSTM or a neural state space approaches. So LSTM is a pretty popular approach for the recurrent neural network. The ability is to capture the time dependencies of the input signal. So we show a simple layout over here. And in order to create that in the MATLAB environment, we could simply start out by loading the data that we synthesized and collected in the first part. And we're going to jump ahead a little bit to where the networks that we can construct it. This is what we call the deep learning, deep network designer. In here, you will be quickly loading some either pre-constructed network architecture that you can use. In this specific case, because we know it's a regression output from the time sequence input. So what we can do is pick out a sequence-to-sequence network using this graphical way to remove the last 2 layers, which was originally used for classification, and replace it with the ones that are more suitable for a regression output. After constructing this network, I'll be able to build up and run a training process based on this information. So I'm going to jump ahead a little bit more. This is the network we set up and being able to run the training phase. And I should be able to see how the training graph is laid out. So remember this training phase, because I already did a split of my original data into 80-20. So those 20 will be the whole data that will be used for running the simulation. Sorry, testing. As this run through, you probably noticed there are multiple interfaces that I'm showing here. This specifically is the training graph that captures the top part, the accuracy in this case was captured by the RMSE, and the bottom part is the loss function during the training. And the original script that I'm running is using the Life editor, which is very similar to the Jupyter Notebook if you tend to work in Python. Okay, so this would lead to a constructed LSTM that offers me a certain level of accuracy. So we can test the data by calling predict on this network based on the new validation data that we had set aside as a 20%. So it seems to be operating quite okay. The second approach, because we talked about having such design environment, is really helping us to do design exploration in a much more smooth way. In the second approach I'm going to show here is using neural state space. This is a slightly different approach from the early RNN one. In this case, we would like to start out from the classic state space representation. We're going to be using two feed-forward systems or multi-perceptron networks in this case to learn the nonlinear state function, F, as well as the nonlinear output function, G, from the data that we have. And this technique is also known popularly as neural ODE because it really resonate very well with those of us who has worked in control in the past, and really seeing how by this replacement of heavy usage of conv layers and other kind of approaches to really capture the physical inspired meaning behind this type of network. So I'm going to again let the screen capture runs for a little bit. We started out with identical fashions for driving the validation data by splitting them 80-20 split. And then we're going to be taking some down samples for this network. And one thing I do want to call out in here is, relatively speaking, training a neural ODE model is relatively slower comparing to that of the LSTM network we support. But in the early examples, I would be able to speed it up by having a GPU. And in this case, I'm not using the GPU and direct the CPU to train this network. So the setting up this network, we have a lot of pre-canned capabilities as well. Feel free to look into our documentation and find out some of the examples to do it. But here I'm really trying to illustrate these cases by someone who's probably not a domain expert in this case for deep learning specialist, but more like someone of us like a control engineers. So here you will see the training loss during the training phase is also reducing, and also it's advancing in a way that is slightly different from how the epoch was set up in the LSTM network. Okay. So with this, I now have a new network. And in this network, we also get in to be able to run the test. And you may notice the test run. So I'm going to run this particular session. You may notice the RMSE is slightly worse comparing to that with the LSTM network that we had before. This is, again, reminder, this is based on the testing data we have around here. Okay. So this is the output from the trained network in this case. So now we've done data preparation, AI modeling. The next step we want to take is being able to simulate them. The ability to drop this type of construct directly into a Simulink model so that we can run feed-forward system by testing them with the real data that we use to just like how we generate them, and then being able to run a closed loop simulation to observe how this particular type of network that we constructed be able to interact with the rest of the closed loop elements has been a very important capability and step for us to understand our models a little bit better. So the simulation run for this, again, I'm going to skip the setup stage and directly drive down to the last few pieces. So we'll be able to in this case, I'm going to pause right here. So in this case, this is the signal logging output. As you probably see, multiple network. In this case, the LSTM, the neural ODE has been placed into the Simulink model. And these are the feed-forward output that we get, inference output we get from feeding data in this particular integration model. And then we want to jump into, this is the same simulation actually you saw when we put in the LSTM network into a closed loop system. And you will be able to see, in this case, how we're signaling the output. I'm just going to let this particular part. The leftmost is the original first principle model. We call it SI engine. This is coming from the toolbox, the powertrain toolboxes. The second block, that subsystem you see here, is using the LSTM network that we construct in the early steps. And this one is the neural state space models that we use. So now we can select which one. You probably see some of them graying out. We can select which one become active to act as part of this closed loop simulation. And in this case, the LSTM one is active, and we'll be able to see the simulation output from, in this case, the engine torque based on the different kind of input from the user, the driver's scenario. Okay. Now, as I mentioned, this is a component simulation that we're running our reduced order model methodology on it. So in this case, I will take this model and run a code generation and hopefully put it into my real-time system. Specifically, we can use, in this case, the LSTM example. And I'm going to run a code gen. Sorry, I'm going to hop into. This is automatic code generation from that block, and be able to glide through all of this. And you'll probably see the step function, which is where I'm showing here, that shows how the inference steps going to be taken. This is the collection of the automatic code generator we'll be able to approach. So in this case, this generated code will then be deployed into a real-time computer. So the right side, the gray, the yellowish color of the passenger car model is the one we just worked with, and we're generating code in that model, and we're putting it on generated code onto the real-time computers, and we'll be able to hook them up together, in this case, doing the hardware in the loop simulation and testing. And this is the type of output we'll be able to see from that. Okay, so sorry for rushing a little bit. I jumped ahead in some of the full version of how the workflow is going to be exercised in there, because I want to land into, this is really applying at the design stage, in design exploration, in understanding if now we're ready to use AI-driven and data-driven approaches to represent and model a much more complicated first principle models. These are the steps we can take. Now, we can quickly, I'm only showing two over here. As I mentioned in a lot of diagrams, we have multiple ways to do it. So really, without leaving your desk or moving away from your computer, you're able to do this design exploration. The buttons, well, the colored balls I'm showing here is really just applies to this virtual vehicle example I'm giving. So for example, the model sizes may in this case are still too big for you. So how do we approach that problem? By applying the same AI-driven or data-driven approach to solve the problem. But when our design need is even higher, in order to further compress the design that can be later on deployed into a much more energy constrained system. So this is when I'm going to pass on to Greg for him to talk about the third part of our original of our content. Okay.
Excellent.
And thank you.
Thank you, Brenda. Thank you so much, Brenda, for leading us through that. So Brenda had already showed the AI model development stages that we had talked about. And so I'm really going to focus now here on the right. As we get to the deployment and you do that code generation that Brenda talked about, and you can either target an embedded device like an FPGA or an ARM or a CPU. But we're really going to focus on the edge AI applications. And in order to get there, you need to have some compression. And so this compression that we're talking about here today is pruning and quantization. And we'll go through some of the stages of how you make these decisions and what works best, and then how the need to iterate over this during your development process. So if we start with the problem statement here, we often hear from our users that they have a 600 kilobyte model of learnable parameters, and they need to target something where they only have the ability to load 300 kilobytes of learnable parameters. So in the middle here, what can we do? What are the knobs we can turn in order to reduce the size of this without affecting the accuracy of the model too much? So you can see here we show structural compression and then quantization, and we're going to get into the details of this. And then, at the end, we have code generation for our specific target. So the workflow steps to compress the deep neural networks. First of all, it's to understand your hardware constraints. So oftentimes we have a hardware device in mind, or at least a limited subset of hardware devices in mind. So we can take and choose a model from Deep Network Designer. And what you do is you'd select one that gave you enough accuracy for your system, but wasn't too bloated to start with. We always want to start with something that's not much bigger than we know we need in terms of accuracy. Then we move into pruning. And here we show a Taylor prunable object that's being generated. And we'll talk about that. And then finally, we can change the data types so that we have smaller containers through quantization and reduce the size of our learnable parameters through smaller data types. And then we have the deployment and integration of the system. So if you look at some of the literature out here, there's quite a bit. This is a picture from Cornell University. And there's really a lot of different approaches. So this is just an overall framework, and there's not really a good comparison between them. But there are some general aspects. So there's like scoring. So we have the absolute or gradient-based scoring, and this is dependent on how much data you need for these and how much time it will take to execute this versus the effect it'll have on your network, how much it will reduce your accuracy. And then the size of that, so you had an original training data set, but how much retraining data set do you need in order to determine the importance of these weights? And then we move on to the pruning criteria. Like, are you going to do this on a local level or is it global pruning? And then finally, fine tuning is next. Should we do fine tuning? There's literature both ways. And then finally, the scheduling. Is it one shot or is it iterative? So there's no clear winners, but there are definitely some guidelines for best practices. And so we found that global pruning, definitely will see some approaches that need some fine tuning, and an iterative approach to this as well is important. So what parts of your network can be pruned? So there's 3 different aspects here. The first one is the unstructured element-wise pruning, which is really going to introduce sparsity. And this is not going to reduce the memory impact of your network. This is only really going to have an inference speed up, but only if your hardware has the ability to understand this and take advantage of it, or if you have some specialized libraries to do that. In the middle, we have structured pruning, so either channel, shape, or filter-wise. So you can think about this. We'll show an example where we prune full convolution filters. And on the right one, we're not going to focus on today, but you could remove whole layers. And obviously that will physically reduce the size of your network. So specifically Taylor pruning. So we use Taylor approximation pruning. It uses first order Taylor expansion, and it grades the filters, the convolution filters, in terms of their importance to the accuracy. And then we prune the less important filters. And you can see here on the right, there's the green line, and that's over 16 pruning iterations and the number of prunable convolution layers that are remaining after we prune through each iteration. And then in the middle is the blue, and you can see the accuracy. And so it's doing pretty well. And then we get to a point where it starts to tail off. So even with retraining and fine tuning, you're not able to recover all the accuracy. Next, we have parameter pruning to zero out the lower score connections. And so we can rank these as well and then in your network. And so it iteratively removes the less important connections. So some examples are magnitude or sin flow scoring. And you can see here on the left, there's a plot of the blue line is the original network. So it's high accuracy. And the green and red are magnitude and sin flow scoring. And you can see they pretty much are holding up in terms of accuracy as we get up to 40% sparsity. But after that, they both degrade at different rates. until the network's accuracy is pretty low. So in terms of the structural pruning, we can, if we do projected layer pruning, it really reduces the problem space. And so if you look at this LSTM network, we can break it down and determine what aspects can be removed. For illustrative purposes here, you can see on the bottom, that's a wave image that's pretty clear here. But if we want to reduce the size of that and still know what it is, we can remove a lot of the detail. So you can still see on that right image that it's still perceived as a wave, but a lot of the detail is gone. So the water droplets are gone and some of the different shadings of color are gone. So this projected pruning that we showed in the previous slide there, it's with neuron principal component analysis. And so if you look at this fully connected layer here, is this really needed? There's a high number of inputs and outputs, and a lot of it's underutilized for the inference purposes. So we can take this model, this layer, and do a projection into a subspace, and this will give us a projected layer of that LSTM. And then from there, we can do neuron principal component analysis, and then determine how much we can reduce the size of this model. So next, I'm going to walk through just a quick screen show, like Brenda did here, on the structural compression when using projected layer pruning. Then this focuses on LSTM layers. This example uses the Japanese vowel dataset, and this approach would work on stacked LSTM layers or single LSTM layers. So we'll see how this goes here. So the first thing we do is load our network. You can see there's 4 layers, and we will go through and generate the neuron PCA object. From there, we can analyze the NPCA and see the input and output eigenvectors and values. From there, we can actually go in and do the projected pruning on the PCA object. There we go. And you can see the original accuracy of the model is 91%. And then after we did the projected pruning, it's down to 48%. So pretty big, a significant drop. We can see that here in a bar graph here, that this is a good drop. However, the number of learnables is reduced significantly as well. So we're going to have to do that retraining. We're going to have to fine tune it in order to get it back. So you could also look at a specific memory requirement and then back into an amount of compression that you need, and then look at the explained variance and see where that falls in the plot, and then do compression to that point. So we'll see here now that we'll go back through and do some retraining. So we found that oftentimes you can do fewer epochs of retraining for the fine tuning. So here we're going to do 30 epochs, and then you'll see the loss output for this model. And then finally, you should see the accuracy of the fine tune is back up to 91%. So you can see here a plot of those accuracies, and I'll break it down for you here a little bit better. On the right, you can see the accuracy is reduced by 0.3% after, there was an original, and it projected pruning significantly reduced, and then when we fine-tuned it, we were able to get back that up to within 0.3% of the original model. The number of learnables is reduced significantly by 82%, and you can see it in moving from the projected to the fine-tuned projected that hasn't changed because we're not removing anymore, so that makes sense. And then finally, the inference speed, the max execution time is 42% faster. So this is a significant improvement for our edge AI deployments. And you can get this example in our documentation on the web. Next, so we've done all our pruning. Now, what about our data types and our quantization? Can we reduce this from this traditional floating point 32 to int8 data type containers? So the first thing we do is run this network with a representative data set through calibration, and we can see the weights, biases, and activations and the range of the data that's coming through. And the way that we interpret this is the blue is with the int8 data type that's container that's chosen for this activation, what's representable. So the intensity of the blue means how often you're going to see that data. And then the gray is a non-representable data. And then the intensity of that is how frequent we will see that in the data. We can go through and do validation on this and actually implement the quantization into the model. And we can see that our accuracy our learnable parameters is reduced by 75%, and our accuracy is only reduced by 0.3%. So that's good results. I need a delay here. Hold on. There we go. So finally, looking at this, so this is the number of learnables on the left plot. So the original network has a significant amount of learnables. We reduced that with the Taylor pruning, slight more reduction in the parameter pruning, and the quantization is the same. On the right, we see that the original model, the Taylor prune model is in terms of the parameter memory is reduced significantly, slightly with the parameter pruning, and then with the quantization we can remove that, reduce that even further. So in summary here, we've seen how to start. Brenda showed us how to, starting with a design of experiments, we can create a suitable synthetic data set, and we can use that for training our AI models. And then such models, including the deep learning techniques we showed, but also there's system identification with the engine example of the machine learning models that can be used to replace parts of the complex dynamics of a vehicle. And then we've integrated this AI model into Simulink for system level simulation, together with first principle components. And we showed some generation of C code and performing hardware in the loop testing, always important. And then finally, we went through some of the pruning and quantization techniques that are effective for edge AI deployment. And you can and some of the iterative nature of that work. So with that, we thank everyone for attending today. And I think that Danila, we can open it up to questions.
Sure. Thanks so much, Brenda and Greg, for your great talk. Very much appreciated. And also thanks to Dor for prompt help in answering a question that was posed early on to the Q&A window. I encourage everyone to attending to pose questions to Brenda and Greg. But in the meanwhile, maybe someone pose these questions. I would like, if you can go back a little bit, Brenda, before I request the controller. I have a question for you. You know, designing neural networks require also the capability to set the hyperparameters. And sometimes these require a lot of experience. And it may happen that engineers in small, medium enterprises, maybe freshmen, do not have such expertise. And they would like a kind of automated method to tune the parameter. Can you talk a little bit more about MATLAB capabilities to handle the parameter optimization? Is there any facility that you offer?
Let me make sure I unmute myself and then change the slides back into. Okay. Thanks, Danilo, for that question. You're quite accurate in the sense of that a lot of our engineering principles does not teach us how to start out by dealing with the complicated systems like deep learning network, and especially training and tuning the hyperparameters for those models. So indeed, in MathWorks, we start out with a very visual tool that we call the experiment manager. Means we want to be able to build up the experiment that can be used for how you want to tune those parameters. In addition to that, because MathWorks already have toolboxes like global optimization toolboxes. So we also offer the capabilities to, for example, using Bayesian optimization as a way to automatically tuning and finding the right hyperparameter choices. And those ones can also apply to, for example, identify whether the network architecture needs to be bigger or smaller based on the training data. And all of those phases can be packaged around and run it in a much more kind of headless way. In that case, you can put it in a worker in your clusters, so that will be run automatically and come back with the answer. Actually, this is one of the things that Danilo and I had some starting out some collaboration, and we find that marrying this methodology together with the ability to quickly iterate how the resulting design can be applied to environment like a microprocessor, in this case, utilizing the dev cloud with ST provided, has shown a lot of great results. So I'm actually quite excited to maybe in the future months to be able to share some of those results as well. And that's kind of how powerful we can go just by offering the tools to people who are probably just starting out in this. And also, I have to emphasize that, MathWorks have a lot of ramp up as well as training materials that's available online, and you can get to many different facades of our tools by following some of those as well. Thanks for your question, Danilo.
And thanks also for your elaboration, Brenda. There is a question that Dory is, I think, already answered. So I have a question for Greg. In the meanwhile, someone else will ask anything to you. Greg, there are methods to decompose convolutions and dense layers in order to reduce their complexity at some cost of the accuracy. I wonder if these kind of methods are supported by the deep learning tool you provide.
So, I mean, you can do it. You could do it by hand yourself in terms of actual features or functions that are enabled for that. It would really be using the projected layer pruning in order to break down your network. And so that would be supported for LSTM layers as well as fully connected layers, and coming soon GRU layers. And so that would enable you to take a matrix and break it down into a couple smaller matrices, and then reduce the dimensionality of those to physically remove parts of the network.
Okay.
I don't know, Brenda, if you could elaborate.
No, I think that's that's to the point. Yeah.
Okay.
That's great. Then, Brenda, a question. I don't know if it is quick or need more elaboration, but this is something really I am curious. I know you are an expert of motor control, and each one has got his own style in driving a vehicle or using in a particular way an electric motor or also a thermal motor. So it's difficult sometimes to generalize, to find a general model that adapt to everyone's style, which means that sometimes maybe on-device learning can be of help. So, I'm chairing the on-device learning working group on behalf of the tinyML Foundation. I was wondering if on-device learning is something in your radar for future development, if you see a need to support it, and what is your opinion in general on the topic?
So I would claim no expert to be knowing all the state of the art for what we are, but coming from MathWorks, yes, we're actively investing this area, just like how Danilo, you and your group encountered this being a very realistic challenges when it comes to deploy kind of replacement model or AI approach to those, is how do we adapt to the huge variety of the instances that we have out there, especially for edge. So on-device learning translates to us in really three elements. One is at the modeling designing stage. That means we have to accommodate for different kind of parameters. So even though it's very difficult to generalize, we would like to have the ways to being able to model those. And then the second step we take is really very much of a statistics and machine learning approach to handle this problem. That means we'll be able to train our model, and when we put our models together, we understand there is a need for updating it later on. So that really leads to the third part. As I showed, we have automatic code generation capability. So that means the software, the embedded software will automatically generate it, also carries the structure of the fact that this design would be able to be updated, like over-the-air update, also as well as the ability to react to new information in a learning fashion. Now, this is very active research and also very active, I would say, development areas, competitive as well. So we do have colleagues who may have interesting results to report out, and we'll have ongoing discussions with our users specifically to be able to make sure we capture the requirement at the first front. So yes, we definitely have something in the pipeline. And yes, we really love to get engaged with you and your working group so that we could get to the latest and state-of-the-art work coming out of it. And also, we would be more than happy to share our progresses with the tinyML community, either in a forum like this or in other trade shows or summit meetings, for example.
That's great, Brenda. Certainly in a future event of on-device learning, I will keep in mind to contact you back on this topic and see what you can offer, because I think it would be ultra important to contribute. Yes, it's a research subject that really the community is looking to make it happen sooner than later. So your contribution will be fundamental. Having said that, since I don't see any other question from the attendees, first of all, let me thank so much for your great talk, Brenda, Greg, and also for the help of Dora, which was much appreciated. I think it was super useful to have your time and your contribution to the tinyML Talks series, and once again, very grateful for your availability. Let me request the control so that we complete the session. Okay. So as said at the beginning, these a series of talks, as well as the other events that the tinyML Foundation organized, can happen thanks to the tinyML strategic partners' commitment to support all these activities and to make sure that the community is alive and eager to share any development concern on the tinyML topic. So let me remind who are the executive strategic partners. Qualcomm, Symbian, the Platinum strategic partners that are Renesas, Aetrios, Sony, sorry. Gold strategic partners are Analog Devices, Arduino, ARM, Edge Impulse, Infineon, Innatera, Microsoft, Sensimil, ST Microelectronics, Synaptics, and all the silver strategic partners. Quickly reminding ASVIP, BrainChip, Green Waves Technologies, Grotherty, IBM, ImageMob, Not AI NXP, Poly Technology, Pitso, Schneider Electric, Silicon Labs, and TDK in the center. Last but not least, let me thanks a lot Olga for her great support in all the phases that conducted us this event. And let's keep in touch soon for the next talk. Thanks again, Brenda, Greg, and Don.